Right. So so let's continue with the causation theories. Let me formally define, because this is one of the things that were not very clear in the previous versions of the paper. So the ingredients of these causation theories, of what I'm calling causation theories, they are like, first you need to believe that a certain unobservable factor exists. So that's the first dark matter in this type of theory. And these unobservable factors, they can be, for example, costly reversibility of investment, mispricing, low information, expected cash flow duration, whatever you want to think about. This is going to be this is the unmeasurable part of the theory, the thing that you kind of need to believe that exists. There's going to be the V for value, S for size, and what you have in this type of what you have in this type of theory, and that's why I'm calling this causation theories, is that changes in this variable here. For example, if a firm increases cash flow duration or decrease, I don't know exactly what the story is there, but this is going to have an impact on the risk of the firm. So if cash flow duration decreases, the risk of the firm increases or decreases or whatever goes on in this story. If you have more information about the firm exogenously for some reason, then you're going to lower the risk of the firm. So this is why I say that this is a causal theory in this sense. It's because changes in this variable, in these unobservable variables, they cause changes in the risk of the firm. So that's the first part of the theory. That's the first step in this type of theory. Then you have a second step, and the second step is the claim that this unobservable factor here, it's a bit more of dark matter. It's this unobservable factor is actually related to book to market. So they make the claim that in these theories that, for example, low information is related to the size, to the price of the firm, or expected cash flow duration is related to the risk of the firm. Sorry, it's basically it's like low information is about the sizing, so it would be related to price. Cash flow duration, I think, it is related to book to market. So there is a function that links this type of the unobservable factor to book to market, or costly reversibility is the same type of story. So what you have is then one function that links the unobservable factor to risk. That's a causal relation here. And then you have something that it doesn't need to be causal. Actually, it could be just a correlation study, but there must be a link between book to market and this unobservable factor. And now, because you have this function and you have this function, if you had everything as linear functions here, you would have the decomposition of a linear function is also a linear function. What you essentially, and that's the basic thing that uh, these theories do, what you essentially do is you intrinsically link the two things. You have now intrinsic relation between risk and book to market. It's not a causal risk, so book to market can change without causing changes in risk. That's important because when one referee also asked, but does it mean that changing in book to market causes changes in risk? No, it doesn't. It doesn't need to be like that. That's the workaround that these guys have. They say, oh, it's not exactly book to market causing risk. It's this other thing that we cannot measure that causes changes in risk. So it's okay. It could be this unobservable factor here causing changes in both. But the point is still that the two are intrinsically related. So if this causes a change in risk, it also causes a change in book to market, or is related, it is correlated with a change in book to market. Then you have that the relation is maintained. If they are linear functions, then you like all this ugly thing here is just to say that this is a linear function of this, and there's a linear relation between them. Now, what this accomplishes. So let me just go back. What this accomplishes is that form of describing the risk of individual firms as a function of these two firm characteristics that I called kappa before. So it's the same idea. And that's why later it's going to give you the same observable results. This type of theory, they are also tailored in a way that fits the Fama and French model very well. Because now we can have that the premiums, the SMB and HML premiums, they are claimed to validate the theories, and also the theories are claimed to validate the risk adjustment based on SMB and HML. Because now the portfolios, if it is true that this happens, then it's clear, as I kind of already discussed earlier, it's clear that um, oh, sorry, it's clear that this risk is going to capture the same latent factor exposure. If this is true, also if this risk adjustment is valid, then the regression intercepts they are going to allow for inference about factor zoo or excess return and so on, and all types of conclusions that usually arise from running Fama and French type of regressions and looking at intercepts. These conclusions are only valid if the factors actually control for risk. What is also important, and that's the point of a static version, is that there's no testable differences within this group of theories. So all these groups, they have different stories about what goes on, what exactly, like all these costly reversibility, mispricing, like from all of them have different stories about how to link one unobservable variable to risk, different unobservable variables to risk, and essentially you cannot tell which one is right because basically because they are based on this dark matter type of assumption. So you really cannot tell which one is right and which one is wrong. They have the same they have the same empirical implications. What ends up happening then is that there's a multitude of these theories, and each of them tells that they are pinning down the one correct missing factor. And then you have different groups believing in different groups of theories, or depending on which group you belong to, you believe in one theory. It's also important that this is untestable against the correlation theory too. So we cannot tell which of the theories among these ones in this group that I call them causation theories. You cannot tell which of the causation theories is right, and you can also tell whether causation or the correlation theory is correct because they just predict a premium related to SMB and HML portfolios, all of them in a static setting. Again, as before, I go to the intertemporal setting and then I look for differences in these theories. And here is where I need to make also an assumption about the dark matter assumptions that these theories, these eventual intertemporal theories are going to have. And the assumption that I make is an assumption of parsimony. So I want a parsimonious model that doesn't claim that there are more than very minimum changes according to the price of risk. So for example, and these are important to get the results to get the implications that I use. I'm going to assume something like the theory is unconditional. Unconditional in a sense that in high price of risk states, the only thing that changes is the price of risk, the level of the price of risk. So this is a vector with a bunch of elements. And what I'm saying is that this vector is just multiplied by a certain constant here that's bigger than 1. So all the elements in the vector, they're multiplied by the same number, meaning that the relative risk prices, they stay the same in high and low price of risk states. So if one asset is, one type of shock has a high risk in low price of risk state, the same shock has a high price of risk in, the same shock is going to have a low price of risk in high price of risk states. So I don't know if I said it right. The shock that has a low price of risk in one state has a low price of risk in the other also. It's just that the level of the risk in one state is higher than in the other. I also assume that there are only 2 states, so this is a simplification. So there are like these 2 states. And another important point is that it's what I say. Well, here I assume that there are only 2 states really, but this is consistent. This is actually extendable to assuming that the price of risk is actually random, as long as it doesn't change systematically. So the risk of the individual shocks, the price of risks for the individual shocks cannot change systematically with the price of risk. So that's the first assumption that I make about the dark matter in this type of theories, because the problem is that these theories, they're all static. So, and then I need to assume something about what they might assume regarding that happens intertemporally. Right. So this is the first thing. I assume that they use a parsimonious model like this. They also use a parsimonious model to indicate how the variable, how the firm characteristic is linked to risk. So this BT here is the equivalent to that BT that I showed here. So this the causation theories, they also have the same type of it's exactly the same, right? So they also imply this. And BT tells you how much the risk is related to the firm characteristic. And what I'm saying is that in causation theories, there's going to be like, depending on whether you're large or small, for example, you're going to be exposed to a certain shock. And and BT gives you the amount of exposure that you get for each, let's say, unit of each dollar that you have of price. And what I'm saying is that this BT here for price or for book to market doesn't change systematically with the price of risk. It may change with something else, but not with the price of risk. Right. So in high price of risk, in low price of risk states, it's always the expectation is the same. It can vary. It just has the same expectation. The second thing is it's like a parsimonious extended, let's say, parsimonious assumption, which is that the parsimonious assumption would be that the price spread in high price of risk states would be just the same as the price spread in low price of risk states. Price is a bit problematic because it's non-stationary, so it's probably easier to think in terms of book to market. So the book to market spread in high price of risk states would be just the same as the book to market in low price of risk. That would be the most parsimonious model that we could think of. Like if I want to apply the same type um, reason that I used here, then it would be that, right? It would be high price of state, low price of state, the spreads in the it's not the spread in book to market actually, right? It's the spread in this underlying whatever is the factor that they chose to explain these factors here. It's the spread in this thing here in this unobservable factor is going to imply a certain spread in the firms, in the risk of the firms. And what I'm saying is that this spread can either be the same in low and high price of risk states. So it would be equal to 1. So everything here would be equal to 1, QP and QBM would be equal to 1, and they would be the same in both price of risk states. Or, and that's I'm putting the extended part here, the book to market spread increases in high price of risk states systematically. The reason for this is basically to account for the assumption in Zhang 2005 paper, in which book-to-market spreads actually systematically increasing in high price risk states. So if this is the case, if we are going to assume to make this assumption that book-to-market spreads increase in high price risk states, then at least I want to make the assumption that they don't increase by less than the size spread. So if it's going to increase, it's going to be relevant enough for it to not be smaller than what happens to the spreading price. Now, this is almost unmeasurable also, right? Because price is non-stationary. So how are you going to actually compare this type of assumption? That's also why I'm not sure exactly how this type of theories can link some underlying factor here to risk. And well, anyway, the point is that if the spread is going to increase, it's going to increase by more in high book to market states. All right. So now that I have these assumptions, these parsimonious assumptions here, and extended parsimonious assumptions here, now I can get the rejectable implications from the theory. Because now it's very easy, right? Now what I basically have is that in high price of risk states, whoever is riskier is going to continue to be riskier by the same amount, and the price of risk increases, so the premium is going to increase, right? So all of this is basically to get this result here, the result that the spread between the HML and SMB portfolios is going to, when the price of risk is high, is going to be bigger minus the spread when it's low is bigger than 0, which means that this spread here, when the price of risk is high, is larger than the spread when the price of risk is low. And that's basically saying just that, well, if value is riskier than size, then the risk premium needs to increase with the price of risk. The difference in risk premium between the two of them needs to increase with the price of risk. So that's the point here. How do I show this? Well, just calculate the expected return on the HML in low price of risk states. It's going to be equal to this, approximately equal to this. It has a narrow term here, which is 0, because this is, remember that this is the risk of the portfolio is going to be BT and the book to market spread. That's why the book to market spread before was important, because it gives the changes in risk. So that's the risk in low price of risk states multiplied by the price of risk. So you get the risk premium. In high price of risk states, this is going to be multiplied by QM. So it's the same thing. And this is going to be multiplied by this is Q lambda, and this is going to be multiplied by QM. So you have that the risk premium high price of risk states is just a multiple of the premium in low price of risk states. Same thing for the S&P portfolio. And here is why the assumption for that the increase in book to market is important to be at least the same as the increase in the price spread, because now this QBM needs to be at least the same as QP. So if this is true, then we know that this is going to increase, right? That's basically why I have this assumption, this extra assumption. In a way that I'm still able to reject the type of theory like Zhang that says that book to market spreads increase in high price of risk states. So what happens then? Well, this is what we already have. And because the HML premium is proportional to the price of risk, you can think about it, not exactly, but you can think about it as when you look at further qualitative evidence that it's almost like HML is in now changes. You change the HML to cents and the S&P to dollars. And then when you regress a variable in cents on a variable in dollars, then of course what's going to happen, what immediately is going to happen is that, well, first now this variable is much larger than this, so the intercept is going to increase. The intercept in high price of risk state is going to increase. The beta is also going to increase, and but the R square is going to be the same, right? You're just multiplying this, but it's not really in cents and dollars, because this one is multiplied by one number. This one is also multiplied by a number, and both of them can be multiplied by a number that's more than 1. And if this is true, well, HML is always multiplied by more than 1. S&P may be multiplied by more than 1 if the spread also increases here, for example, or just because the premium increases. So what this means is that, first of all, if you look at the beta in low price of risk states, the beta is going to be smaller. Like imagine that you're regressing HML on S&P. So you're looking at this beta here. The beta is going to be smaller when this one is not multiplied yet, when both of them are not multiplied yet by these big numbers. So you have a small beta. This one is bigger. Now the beta is going to be bigger because it became bigger relatively, even bigger than the S&P might have become bigger. So the beta is larger now. The S&P beta is going to be smaller because HML is now a bit bigger than it was relative to S&P. Let me skip this. There's no change in the risk exposure, right? So because there's no change in the risk exposure, the composition of the portfolios don't change, then the R squared needs to be the same. The other point here, and that's the one that is not exactly clear, and that's a point that's not exactly clear, is that what happens to the HML alpha in both states. Sorry, the HML alpha is actually correct, right? The HML alpha is going to increase. In high price risk state is going to be bigger, exactly for the same reason there. The alpha of the S&P portfolio is one that we cannot tell anything about. And the reason is because, well, you don't know what's going to happen with the S&P portfolio. The S&P portfolio can increase. For example, if the spread continues the same, the S&P increases. The beta decreases, so maybe the alpha is also going to increase, right? So that's why the alpha, you don't have any implications for the alpha, for the S&P portfolio alpha in this spanning regression. Uh, and what's important, and that's the main point of this part, is that all of this, except this one in brackets, all of these, they are different from what the correlation theory implies. The correlation theory implies that this is the opposite, this is the opposite, and the R square is much higher in high pressure risk states than in low pressure risk states. So we can tell which one, not exactly as a test like here, but you can tell which one is qualitatively consistent with the evidence based on that. All right, let me have a break and give you the results.